First, what we're going to do is we're going to open up MCalibration. So I have it here. 1 second. I pulled up MCalibration. And this is the screen you get when you open it up. And I'm going to point out a few options here. So first, we have our general. We have the menu up here, and then really we have 5 tabs down here, which are of the most interest. First is this welcome, where you have recent MCalibration files. The next one over here on the left is tutorials. This has a bunch of PDF tutorials that we've put together that cover different topics. Those can all be seen here. There's also a couple links down here for some interesting ones. There's the MCal intro, which is a very valuable document. We also have a couple of videos here that you can watch. We're going to skip over this data for now. We're going to go to the main MCalibration screen, which is Calibrate, which is down here over on the left. So I click there, and we pop up a new window. This is the main window of MCalibration, and this is what we'll be spending most of our time in whenever you're using MCalibration. And I'd say there are 4 main parts. There's the window here, which will hold all our experimental data, our test data. Down here, there is a window that will have information on the material model that we're going to calibrate to our data. Over here, we have a plot for the experimental data and the predictions. And then we have some output windows here. So I always feel the best way to demonstrate capabilities and talk about how to use it is to go through an example. So that's what we're going to start with. So I'm going to bring over a little window here. So this is just a Windows Explorer window that I have some files set up in. We're going to start here with exercise 1, and we're going to go through the entire process. So I'm going to copy this here. And so the first thing we're going to go over is how you get experimental data into MCalibration. So I'm going to come over here and we're going to demonstrate multiple ways we can do this, and we'll start with the most cumbersome and eventually get to easier methods. But I'm going to start by hitting this plus. This plus adds a load case, and a load case is the term we use to describe a set of one experimental run that we're using in MCalibration. So I'll hit this plus, and a window will pop up that says load case setup. There are a whole bunch of options to go through, and we'll walk through them slowly so you can understand what they are. But first, there's this load case type. Experimental data is the most general. You need to specify 3 different things, 3 different pieces of data: time, stress, and strain. If you come here, you see there are a whole bunch of others, but we'll spend most of our time today with experimental data and drop into a few because those are really the introductory ones. To get the load file, I'm going to hit load experimental file, and I get a normal pop-up. I'm just going to go to that window that we discussed, folder that we discussed. You can see here I've got 3 CSV files. MCalibration works by taking text files of some form or another, either .txt, .csv, or tab delimited files in. The example we're going to show here is for a neoprene rubber for uniaxial data, biaxial data, and planar tension data. So I'm going to start with the uniaxial data, and I'll just hit open. And I get a window that pops up. This is some import of the experimental data. You can see I've got the name of the file here, how many rows and columns are in the data. I can tell it if I want to include or exclude a certain number of rows. And there's a button here for View Data File, which I'm going to click. And this shows us what is in that text file that we open. So this is just a little mini text file viewer that's included. You see we've got some column names here. We've got a header here that has percents. It tells you, you can see that this data here is pretty old. We've been using this data for a while. It's from 2014. I've got some information here that the column 1 is engineering stress, column 2 is engineering strain. And so that's pretty important for us. We know the first column is stress, second column is strain, and in this case we're using engineering, not true. So I'm just going to hit save. And then you can see that I need to tell MCalibration which which columns are the stress and which ones are the strain. So if you remember from our file, the strain was column 2 and the stress is column 1. I only have 2 columns, but there's also ways here that you can bring in time, transverse strain, and temperature. We'll get to a time column later, but for now we're just going to start with these simple time, strain, and stress. So I've specified strain and stress, and I hit OK. In this case, we didn't specify times, but MCalibration needs to know the time that this experiment happens over. So sometimes that's not included in the experimental data. So when that's the case, MCalibration asks you what strain rate the test was performed at. That way it can then calculate the time based on the strain that you give it. So for this simple example, we're going to do everything at a constant similar strain rate, and we'll just use a default of 0.01. So hit OK. So I have a little plot here for this experimental data. I can play with what I see on the Y and X axis. You can see here I've got stress versus strain. I can look at time, temperature, etc. I have some settings as well over in this area. I can tell MCalibration whether this was a strain control or stress control test, and I can also say whether or not this is engineering strain or engineering stress. I have someone requesting to be made the presenter. I'm not sure why I would do that. So if you're having an issue, please please put something else in there so we can figure out what that issue is. Sorry for that digression. So we can go for strain type. We can tell whether it's engineering strain or true strain, and true strain. We also have the option to tell it whether this is percent engineering strain or true strain. For our test data, this is all engineering strain. We have a similar option for engineering stress. There's also something here to specify the temperature. All of these were done at room temperature. We're not going to get into any temperature calibrations here, but you could say that this was 300 K or 150 K if you were colder, but we're just going to leave it at 293. These next couple tabs we'll go through in order here. So this next one is loading mode. So again, this was a so in this one we've done uniaxial tension. We can see that because it's stress, positive stress and positive strain. We come over here to loading mode. I could click on this loading mode. You can see that there are different loading modes we can do. There's unidirectional, there's a film, there's plane strain, simple shear, biaxial, triaxial, and confined compression. And some of these have directions as well. So we can select and calibrate anisotropic material models as well. For this one, we're just going to use uniaxial. We can change the coordinate system here. Again, that's just for anisotropic material data. So I'm going to go over to the next one is time stepping. We'll skip this one for now. We'll get into that in a little bit, what that means and how we can use that in a later example. Next is plot styles. This changes how the data is plotted in MCalibration. We're going to leave it at the default for now. We have a couple other ways we can change that, which I'll go to, but you can set the color, you can change the line width, whether it's a solid or dashed line, markers for data points, things like that. Fitness weights we're going to leave alone. That's really an advanced topic. The last one here is miscellaneous. One thing to keep in mind is that is this solver, which we'll get to later. So I brought in the data. I'm going to change this and just say uniaxial tension. And I brought the data here. I'm going to do that, but I'm going to do it fairly quickly with less explanation for the next 2 load cases. So I'm going to hit new load case, load experimental file, and I'm going to bring in the planar tension. So planar tension, if you're not familiar, is for shear. We're going to check here. Yep, same thing. So stress is the first and the strain is the second column. So hit OK. I want the same strain rate. So I brought the data in. But the next thing we want to come over here to is loading mode. So planar tension is not the same as uniaxial, so we want to come up here and do plane strain. And you can see here plane strain. It's also called planar tension or compression. I'm going to hit save. We've got that one in. I'd like to rename this one. So what I'm going to do, I've selected this, and I'm going to hit F2 for rename, and then I can type in whatever I want. Planar tension. I'm going to add one more load case, and that's going to be the biaxial. Same columns for stress and strain. I'll hit OK. Same strain rate. I'll come here to loading mode, and for this one, we need to choose biaxial. And again, I'll rename that biaxial. So now let's talk about what's on the plot here. So right now our plot is showing true stress versus true strain, and everything is shown in red. So it's really hard to distinguish what each one of these is. We could come in and edit the load case by double-clicking on it and changing the plot styles here how we want. But another nice trick that you can do is if we select multiple load cases, and if you hit Control-E, E for edit load case, you get a dialog box that'll change settings for multiple load cases at the same time. So we can do nice things and say, I can say make color code based on load case index. And there we go. We've got 3 different colors for the loads. I could also come in here and say I want the experimental data to be solid lines and predicted data to be dashed lines. You can reset the temperature if you want for all these. So there are lots of different things you can do here. So I've got the data. Now I can see the biaxial is the green one here. That's stiffer than my planar tension or the uniaxial tension, which is what you would expect for the real material. But I'm looking at this in true stress and true strain, which is not what I input. I input engineering stress and engineering strain. So the first question is, if we have engineering stress and engineering strain, how does MCalibration convert that? For experimental data, it assumes that the Poisson's ratio is 0.5 or that we have an isochoric deformation, and uses typical equations to do that. So now if I want to change this, all these buttons here allow me to change plot settings. This one here is for true stress versus true strain. This one does engineering stress versus engineering strain. I can do engineering stress versus time. I can also select one of these if I want to look at a different response to the material. I can look at maybe, you can choose any of these for what you want to plot, and you can also change the maximum and mins that are seen. So we've got our data in here, we've looked at it. Now we want to select and calibrate a material model. So I'm going to come in here and I'm going to go set material model. And that brings up this large dialog box that lets me see all the material models that I can select and calibrate. We've tried to organize these for you. First up here is the Varus material database. These are pre-calibrated material models for all these materials that you see here. This is a product that we sell as well. And if you click on any of them, it gives you a little bit of information about it. And there's also a PDF that you can look at. So I'm just going to minimize that. And then the next couple sets are, the next set is polyUMOD models. So these are models in our polyUMOD material library for advanced polymer modeling. So these are all the models that we have created ourselves that can be calibrated to different types of materials. So if you come in here, you can see a little bit about them, some of the parameters that you need, some tips and tricks on which things you do or don't need to search for. You can see that as we get progressively down here, you get more and more complicated models. And then if we look beyond that, you can see that we have a bunch of Abacus models built in, a bunch of ANSYS models built in, a good amount of COMSOL models. We also have LS-DYNA and some MARC models. We are going to, what we want to do here for this one is we're going to calibrate a simple hyperelastic model. The easiest way to do that with polyUMOD, which is what I'm interested in, is to use a parallel network model. So in this case, I've chosen a Yo network. I'm going to hit Add. That's all I want to do. We're not going to get into the parallel network model here. It's an advanced material model. But now that I've hit OK, I can see here that I have the parameters for a Yo material model, C10, C20, C30. If I wanted to know what all, and kappa. If I wanted to know what those parameters were, I could come here in the PolyUMod manual, which I'll bring over to my screen here. And you can see that we have all the theory that you could want on how these models work. For this particular model, the Yo model, it's a hyperelastic model. So this is essentially the shear modulus at small strain, and these are higher order terms. And this kappa is the bulk modulus. Right now, this is set up to optimize those that are in red. So any material parameters that are shown here in red will be optimized once we get to that part. You can turn optimization on or off by clicking this here. You can also set lower and upper bounds. We try to be smart and give you good lower and upper bounds. So in this case, we set a lower bound of 0 and no upper bound for these material parameters. So we've chosen a model. We have some default material parameter guesses. And then we're going to hit run once up here. So this is going to, what MCalibration does in the background is it runs a single element, finite element simulation of our experimental data, calculates it based on that material model that we've selected down here, and then plots the results. So we can see here, you know, our initial modulus is okay, but we're kind of overshooting it afterwards. We're getting nonlinearity at a lot lower stress in the actual material. So maybe we want to, so we can come in here and change these values. So I'll change that one, reduce it by an order of magnitude. And I'm going to run it again, and we got a slightly different response. Maybe I make it 1 order of magnitude larger and run that one. And you can see here I'm getting an unstable material model. But we have the beginnings of a model. We have some predictions. So one thing we like to recommend is that you really do spend some time and change these values to get close to your actual material model response. So I'm going to quickly change these to some values. That's a little bit better. But I'm going to come in here. I'm going to let MCalibration do the work for me because I think it'll do pretty good. So I'll hit run calibration. And you can see here, if I come down to the lower right and go to optimization progress, you can see that MCalibration is running a whole bunch of different iterations of this model. And this is the fitness value. So we started up here at about 30. And for NMAD fitness, which sort of normalized mean absolute difference, a 0 would be a perfect fit, and 100 is, you know, you just have an absolutely atrocious fit. So you can see here that as MCalibration went along, it optimized that, and we've come down to something, you know, we're down here at about 6, about an NMAD of 6, and you can read that as a percentage. So a 6% error. That's a pretty good prediction, all things considered. It's going to ask me for, I have it set to save, so it's asking me for a name to save, so I just hit enter. And so if I come here, you can, if I move from the optimization progress to runtime output down here, you can see that the MCalibration prints a whole bunch of statements about what's going on. It tells you, you know, what algorithms it's using. First, it uses a random search, then it goes through the Levenberg-Marquette. And then it goes through some simplex and some NEWUOA. So it uses a whole bunch of different optimization algorithms. And then it comes down here at the end. It tells you that it's done, and the NMAD fitness, and here it is done again. If I look over here at calibrated models, you can see that the model that I used here, that I've calibrated here, has been listed over here, so I can lock it so that I don't change it. Maybe I think this is pretty good, but I want to try some different numbers, but I don't want to erase what I've done. So that's a good way to save it. So we have a prediction. Yeah, so we have a prediction, and it looks pretty good. There are a couple of other preferences that we can set here with this for overall. Sorry, stepping back a second. So I've shown you the basic workflow of MCalibration at this point. We imported some data. In this case, it was all at one strain rate, slow strain rate. We did uniaxial tension, planar tension, biaxial. We selected a material model, in this case, a PolyUMod hyperelastic model, a Yo hyperelastic model. We played around with the initial guesses, but really we let MCalibration do the heavy lifting. This is the material model that we have, and then we calibrated it. So the next question is then, how do you use this? So we've calibrated the material model. Now we want to use this in our simulation. That's either Abacus, ANSYS, or any of LS-DYNA, COMSOL, any of the others supported. So I'm going to come up here and click the Export Model button. So that brings up a dialog box, and then I can choose what I want to, what program I want to export it out to. And so for a lot of these, we have multiple. So you can export an Abacus input file or a Python script. We can do ANSYS APDL commands or their XML format for engineering data. We can also switch the units. You'll see here that we have units. In this case, it's MPA. And we'll get into how you change that overall. But we can tell it to export in different units if we want. So you tell it the 4 units you want, and it'll convert those numbers for you. So I'm going to hit save. Save that file. And now I'm just going to show you what I get. So you can see here, we have for those of you who are familiar with Abacus, this is just standard Abacus command, the density command, the material command, and here are all those material parameters. So that's how we get those out. So now let's talk about some of the overall preferences for MCalibration. So I'm going to come up here to the Preferences button up here. This sets global preferences for MCalibration. You see there are a lot of different things to choose from. The first one's up here, the global options. The first thing to look at is I have this set to use 10 CPUs. There are 16 available on mine. So this can make your calibrations run faster the more CPUs you use, but it never helps you use more CPUs than load cases you have active. So I have this set to 10, but I only have 3 load cases. The most it actually uses is 3. There are a couple other things you can set here. You can set whether you default to engineering stress or and strain versus true stress and strain. You can choose whether you use double or single precision when you export material material models, and you can look through a couple more of those. Other things to look at here in the optimization, we have different optimization methods you can use. We recommend the automatic extensive optimization, which is chosen by default. It really cycles through almost all of these different methods here. There's a quicker one in case you need to do it quickly. It makes the solver not as greedy. Another thing that we've added recently is a genetic algorithm called CMA-ES. So it's down here at the bottom. The genetic algorithm can be useful if your material parameters are not close to what you think will be a good one. So we found that this helps for some models significantly. So sometimes you might want to change that, but we switch between either the CMA-ES or the automatic. There are some other check marks you can boxes you can do, which are pretty self-explanatory. You can choose the function that you use, whether that's the NMAD, the R squared, or some of these other ones. Another thing is this maximum optimization time. I have it set to 0. That means that this would optimize forever if I let it to. If it takes MCalibration a year to optimize it, which it shouldn't take that long, it'll go for a year. You can set a maximum just by putting a time number in there, but if it's 0, it goes forever. We also have settings here for the different finite element codes. We're just going to look at Abacus here, but if you need to call Abacus, there's this Abacus command, and this tells MCalibration where to look for the commands for Abacus. You can tell it whether you want to use double precision or not, whether you should be using hybrid elements or not, whether you should use reduced integration, and then you can tell whether you want, when it writes an Abacus file, you can tell it whether MCalibration should clean up the Abacus files after it's run the simulation, or if you want it to leave it there. And you can also tell it where you want MCalibration to write. You can use the same directory that you're in, or if there's a scratch directory that you want, you can set that here. Down here, there are similar settings for these other materials, for these other FE codes. But next we'll go to units here. By default, at Varus Engineering, we use millimeter Newton second Kelvin units, so that's how I have mine set up. But you can set it to default to whatever unit system you work, whether if you work in meters, newtons, Newton seconds, or millimeters, newtons, milliseconds, or whatever settings you want. We can also go between Kelvin, centigrade, Fahrenheit, and Rankine. And when you change these, you can see that MCal tells you what your units of stress and units of energy are, just in case you want to double check on that. Here's some sound options and some graph options here as well. So you can set defaults and apply a default to the graphs. And then there are some functions in MCal that are advanced that use Python, and this just needs to know where the Python, where your Python resides. So that was the first example, and it was just a simple hyperelastic material model. So I'm going to get into something a little more complex. We're going to use we're going to do a thermoplastic material model. So I've closed that. I'm going to open up a new, excuse me, a new MCalibration file, and I'm going to get into exercise 2. We're gonna do things a little differently this time to show you some different methods. So I'm gonna open up this CSV file. So I opened up that first CSV file just so we can take a look at it. Here you can see, there's some header lines which we have a percent at the beginning, and then I tell myself that column 1 is time. Then we have engineering strain and engineering stress, and you can see that we have data for that. These ones are compressive because they're negative. But so this is how the file looks like before we import it. I'm going to show something that can make it easier. If your files are set up correctly with time, strain, and stress in the first, second, and third columns, we're going to take all 3 of these. I'm going to come back here to calibrate. So I'm going to take all 3 of these. I'm just going to, actually, I'll do it with 2. I'm going to select those 2, and I'm going to drag them over and just let go. And you can see MCalibration has imported those right in there. So I didn't have to do that entire setup that I did for the first one. Another option is I'm going to take this third one here on my keyboard. I'm hitting Control-C. Then I'll click over here and I'll hit Control-V, and it pastes it in. And you can see that I've got the 3 there. I'm going to edit these load cases with the control by coming down here, right click all 3, and I'm going to do color code based on load case index again, so we get 3 different colors so we can understand what's going on. So this is test data on HDPE, I believe. No, sorry, a polypropylene material. So this is compressive data. So we go up to fairly large strain and compression. We go to almost 50%. You'd also see that we have some cyclic data here. So the green one here is a monotonic all the way up to 50%. We're just below that. But the other 2 are cyclic. So we're going to look at one of those a little bit more. So I'm going to come here to this slider. What this slider does is it cycles through the load case. If you have a bunch on but only want to look at one at a time, I'll come here. And so I just want to look at this one. So it's easier to look at. So, in this case, you can see I come maybe to about 5 or 4% strain, and then you can see this drop. So what's going on there? I'm going to hit this button here. This plots engineering stress versus time. And that makes sense. So you can see here I loaded up. I'm not sure what stress or strain I went to, but we were doing a strain controlled experiment. And then you can see I held that stress constant for 30 seconds. So I'm seeing a bunch of stress relaxation. Then I unload to 0 load and reload. And you can see I did that multiple times and finally unload. Another neat feature in this plot area that we've added maybe in the last year or so is there's this button down here which has a 1 on it. I'm going to click that, and you're going to see a second graph show up. So now we can look at 2 graphs at the same time. And this was based on a user request. So anyone who uses the software, if you guys have ideas for improvement, found any bugs, please let us know through our software portal. We're always looking to improve our software. So let me just go there. I'm going to change this one. I want to look at strain versus time. So let's go to engineering strain for the y-axis. Yep. So I'm just dragging here, with left click and drag. So you can see I went up to 4% strain and held that constant. This zooms back. All right. So that's what's going on with that test. I'm going to close that. I'm going to go back to 1. We'll look at stress versus time. So, what else is going on here? I see that these have all been done at, I'm getting a different response. So why is that? If I look at stress versus time, I can see these experiments took very different amounts of time, right? So these were done at 3 different rates. Based on my labeling, you can see that this red one was done at 0.001 strain per second. The blue one was done at 0.1 strain per second, and the green was done in the middle of that, 0.01. So how can I verify that? If I change the y-axis, I can come up here and look at strain rate engineering and see what it looks like. So you can see, so for the blue one, which I said was 0.1, you can see we load up here to 0.1. You get holds where we get 0 strain or very low strain, and then we unload at 0.1. That's why you're seeing these cycles. And if you come up down here, this is the slowest one at 0.001. And then the middle one is at 0.1. So that's great. So now we understand that. So we have 3 compressive load cases here. We're at different rates. So we have rate-dependent material behavior. So we have viscoplasticity going on here. So this material model is going to be a little more complicated than we did before. But let's look at that. So we're going to come down here to set material model and choose a new material model. We're going to stick with poly-U models for all these demonstrations, but there are models in Abacus or ANSYS that could capture most of the features of this behavior as well. So I'm going to come in here and I'm going to choose the 3-network model, I believe. No, sorry, I'm going to choose the TNV. TNV is the 3-network viscoplastic model. This is one of our I believe, the most recent model that we've added to poly-UMod. It's very advanced, but it has a lot of features and is great for capturing the response of elastomers, thermoplastics, composites, biomaterials, all that. There's a lot of theory involved in it. Based on the name, the 3-network viscoplastic model, you could guess that there are 3 parallel rheological networks. Viscoplastic, this is made for capturing viscoplasticity. So I'm going to hit OK. And for this model in particular, there are a lot of options. So we've made a little wizard, I guess you would call it, to show those what you can do. We have default guesses for what you should set for all these. So this is a thermoplastic. So I'm going to hit thermoplastics, isotropic. And these are the settings. So I'm going to hit OK. MCalibration tries to be smart and give me some guesses. So let's see what those guesses give me for a material model. So I hit run. I'm going to hide the legend. So I just right click. I'm going to hide the legend just so it can be a little clearer. I'm going to select these again and make the predicted lines dashed. There we go. So that's not a horrible guess. It's getting some of the features, but it's obviously not perfect right now. An R-squared of 0.65. That's not great, but it was an initial guess. So maybe I need to come in here and change some of these parameters, but you can see that there are a whole lot more parameters than we had before. Now, so I know what all these do because I've used this model multiple times. But one thing but if you aren't sure what they do, and even after reading the manual you aren't sure what they're doing, you could come in here to this Parametric Study button. This is something that we've developed to really help you understand a material model and what's going on. So I changed that value to 20 because MCalibration needs to run here in the background, so I wanted to do that. So I'll explain what's happening. Here we have a table of all the parameters for the material model. So that's what's listed here. And then you see I've got 3 columns for each one of these. This medium value are the value that was in the table when I started. The lower and higher values have been either reduced or increased by 20%. That 20% was based on this number right here. And so they've been decreased or increased by 20%. And we've created a matrix, a little DOE, if you will, for what all these material, these material parameters will do. So it's done running, and I can tell it because I've got all these red, green, and blue boxes. And now I'll come over here. And you see I have a plot. This can be a little confusing, but for this plot, what we're seeing is that first C10 parameter, we've run all three of those load cases that we have turned on, and each one is plotted in either red, green, or blue. And so we can see how this parameter affects the response. So for this C10, see, it really has an effect after yield, what the slope is of this after yield. Now, if I want to look at other ones, I can come in here and look at what tau hat does. Now that is a yield, that's one of the yield stress in this model. So you can see that changes where the material model yields. And then you can go through and look at all sorts of different ones. So M will change some of the rate dependence of the material, or MM, excuse me. So there's another C10, you can see how that affects it. And you can play with this to really understand. So one other thing that I want to talk about here is some tips and tricks on how to make your simulations, your calibrations run faster. So I have here, these were just brought in as I brought them. These data files are brought in the raw data file. If I open this up, you can see that there's 1,000 rows of data. That's actually not too many. That's a good amount for this test. But you might sometimes bring in data that has like 25,000 sets of data. And actually, we'll do a quick example of that. So I've selected this load case. I'm gonna right click and go to Edit Experimental Data. This is another feature in MCalibration. You can modify the raw experimental data that you brought in different ways in case something's wrong with it. I have a plot here. I can look at stress versus strain for the data, and the actual data is here. I could come in and just change these values if I wanted to, but we also have some functions to help change them. One thing that sometimes we have to do is multiply cells. So I can multiply by -1, and now all the strains become positive. I'll set that back. If your data is very noisy, which this isn't very noisy, but there's a little bit of noise, I can come in here and I can select that column and I can say smooth data. You have to be careful with how you smooth here, because if you smooth too much, so if I make this value pretty large, say 100, you'll see that the data changes significantly, and I'm going to be rounding over the corners here. So let me hit OK. Yeah, and that's very different, obviously. That's not representative. So let's undo that. I could smooth this with a small window size, and it did affect it a little bit right there. But this data is pretty clean already. Another thing we can do, which you really need to be careful with, is change the number of data points, and I'm going to do that intentionally. So I'm going to upsample this significantly. So MCalibration is thinking for a second. I now have 15,000 data points. So I hit Save Data to the load case. So if you look down here before, running all three of those simulations took 1.3 seconds. I'm going to hit Run once again. And you can see here it's going to take maybe 4 or 5 seconds. In the grand scheme of things, isn't that long. But we didn't really need it to go that fast. So take that long and take that many steps. So if I wanted to make MCalibration take fewer steps, I could either downsample my data, but that can lead to some issues. Or I can come in here and come into time stepping. By default, MCalibration follows the exact time increments that your test file has. But we can change that. We can tell it that we want it to take less or more if we need to. So I'm going to try 500 here. I'm going to run that selected load case, just that one, and look at it. And that looks okay, but I'm going to actually downsample this significantly. Let's say I try to make it take 50 steps. You see here, it's getting very blocky around here. And that's because it's taking very large time increments. So again, you can and should change this value, but you do want to make sure you're taking enough steps. At this point, I'm going to let the calibration run for a little bit, and we're gonna see how this goes along. So you can see it's making progress. I have pre-calibrated a material model, so you can, which I have here. So I'm going to hit run once. There you go. So you can see I have a material model with an NMAD fitness of 7.77. And if I look at each one of these, predictions are pretty good. If I look at stress versus time, you can see that the model captures some of the stress relaxation. At lower strains, it's better, but at higher strains, it's getting a little bit worse. That's something that we could improve if we wanted to spend more time. But one of the things I wanted to, I brought this one up and wanted to show you the pre-calibrated model is some of the other options. Some things we see, that some users need to take into account. So one thing we haven't talked about is Poisson's ratio or bulk modulus. So in this model, kappa is the bulk modulus. You can see we haven't optimized it because we really don't have any data for the bulk modulus. But MCalibration knows what's going on with that bulk modulus. So I can look at the Poisson's ratio for these materials. So you can see for this, this just shows the prediction, but for these predictions, you can see that MCalibration is predicting a Poisson's ratio maybe 4.2 or 4.3 at the beginning, and then it goes to 0.5. And what if that's not the correct value? So you can change kappa and guess and check to get what you need. But the other way to do it is to add a new load case, and we have one in here called Poisson's ratio. So the Poisson's ratio is obviously it's a very simple load case that we use just to calculate and then optimize against the Poisson's ratio. So you can tell it what the temperature is, what strain you measure this Poisson's ratio out. So it's 0.1% strain. So this is really that small strain Poisson's ratio. And load time essentially gives you the strain rate. So this one would be 0.001 strain per second. And say we measure that that was a 0.38. So I'll hit enter. And I'm going to run that load case. So you can see it does a little prediction here. So these are the results from that. It just loaded it up to 0.001. You can see I have an error of 11.71. And if I hit this I get more information on it. And you can see that I told it the experimental Poisson's ratio was 0.38, and it predicts 0.43. So if I wanted to optimize against that, I would have to turn on some of these kappa values, like that, and then I could rerun the calibration. So get all these, and we'll hit run calibration, and we should see this start to get a little bit better, hopefully. Might take, there we go, there's a little drop. But so this would then optimize and get the Poisson's ratio that matches your actual material. I'm going to switch back to the original one, see how that's going. So this one's still running, but it's looking pretty good. I'm going to stop the calibration, which is that button up there. It's asking me again to save. I want to talk about a couple more buttons here, and then I'll open it up to questions that anyone has here. So we have a lot of buttons over here on the material model side that we haven't talked about. There's also some over here. These duplicate functions that we talked about. But I want to show a couple nice features here. So for some reason you want to scale the material model parameters that you have. You can change that there. These can help you if you've gotten into a bad place with your calibration. You can reset the material model parameters to the initial guess, and you can change some of those scalings. Another thing you can do that is very interesting is check Drucker's stability. So this brings up a dialog box. I'm going to hit run as I described. What you'll see here is it's checking Drucker's stability for this material to see how it goes. And it's testing all these loading modes here: tension, compression, plane strain, tension and compression, etc. And it's testing it up to these strains. And the results are here is that this model is not Drucker stable. So you can see for tension, it's not. So you can come over here to uniaxial tension, and you can see, you have a negative slope, which means it's not Drucker stable. That doesn't necessarily mean this model is incorrect. A lot of thermoplastics show a negative slope there, but that's something to be aware of. If we look at it for compression, it is stable. If we look at it for, let's see, biaxial, almost all the tension ones are probably not going to be stable. Let's look at biaxial compression. So I guess there's a slight negative slope there, but that looks actually pretty good to me. Shear, we're a little unstable as well. But this is a good thing to check in case you, in case you're really worried about that for your material. Other things we can do, you can look at, I hit this little diamond button. You can look at how your material properties change with, in this case, temperature. We have a temperature independent model, but if you had a temperature dependent model, you can look at that. So this shows modulus versus temperature. We have a similar one for loading direction if you have an anisotropic material model. Another button that we have here is a validation button. So this is a feature that we've been building out that can help you determine and make sure your material model works well in a finite element code. So what you do is you can come in here, you choose which code. We have this built for Abacus, ANSYS, and LS-DYNA currently. And then there are different load cases. These run 8 different load cases, implicit and explicit. Some are 2D elements, some are 3D elements. Some of them are pretty simple, some of them get a little more complex. But these just run simulations and make sure that the solver that you've chosen can converge with the values that you've used. And so this is a good check to do. You can set the temperature. You can tell it how many CPUs you want it to use. You can tell it to either delete the files if they complete successfully, or don't clean up any, or clean up all simulation files. I'm not going to run that because that would take maybe 15 minutes to run, and we don't really have time for that. So I believe that brings me to the end of what I'm going to show you today. So to recap, we've talked about MCalibration and the general features and what it can do, and really how you would need to get started with it. We talked about how you can import data into MCalibration, how you can edit that data once it's in there, how you can look at that data. Well, we then talked about choosing a material model in MCalibration. We showed you the list of all the models that we support for Abacus, ANSYS, PolyUmod, and other models, and how to select one. And we showed how to actually calibrate a model. So there's always an initial part where you play with the material parameters, get a good default guess. That's really how you're going to get the best material model. And then we showed the calibration and how it performs. We also talked about some settings on how you export the model and general settings. And then started to get into some of the other advanced loading modes that you can do in there. Oh, one other thing I wanted to show actually before we get on is a very neat feature we have, which we call virtual experiments. So I'm going to hit +V here. This adds virtual tests to MCalibration, so you can see how a material behaves in some other loading modes. So like for this one, I'm going to do uniaxial tension 6 rates. You can see it adds 6 new ones, and I'm going to hit run selected load cases. I'm going to turn these off. So without tension data, this is how this material model would predict tension response at 6 different rates. I'm going to show the legend. So you can see we get rate dependence there. What else can we see? We can see how it does in cyclic tension. So run selected load case. I'm going to hide these. So you can see how in cyclic tension it behaves. And there are a whole bunch of others that you can look at as well. We have some for orthogonal directions, different temperatures, and all of these could be edited. You could come in here and edit some of these if you wanted to. All right, so yes. So that is the end of what I had planned to show you. Please let me know if you have any questions. I'll stay on the line, you know, maybe for, plan is for about 10 minutes, but if questions go longer, I'd be happy to answer them a little bit longer. So thank you for coming to our webinar. We did record it, and we will be putting it on our website, and we'll let you know when it gets there. Please let us know if you have any questions, comments, or feedback on either this webinar or any other webinars or the software itself. And thank you very much for attending. I'll stick around, and if you have any questions, go ahead and type them in, and I will answer them.